All right. Good afternoon. Um, so today I'm gonna work on some examples about dam system with one graph reader. I already posted the study guide for the exam one. Most likely it's gonna be, 2 weeks from now, or maybe 12 days from now. Either Monday or Wednesday, week after. Monday.
Why Monday? We both as a class?
Oh,
yes, we used to.
Yes.
No, it's Monday, it's
Same
the
time.
Monday after.
Oh, okay.
So,
Monday.
it's not the Monday we get back from break.
No, 2 weeks or
Yes,
12
it'd
days.
be the following Monday. So you get more time.
2 weeks of classes. Which one, do we have a date here?
16, March 16.
That would be the Monday that we get back. That would be the Monday we get back.
So you
Not
mean the
even
24th? It was the
You said 2 weeks from
23rd
now.
to the
So
25th.
that would be.
Yeah,
Next
23rd
Friday.
to 25th.
Let's do the 8th. So if you said Monday, that'd be 12 days from now, which would mean. No.
Monday,
the day. You mean Monday, the day we come back from break?
I think
No,
you
3
mean the
weeks, yeah.
23rd and the
Okay,
25th.
okay.
Sorry.
Then he said
Sorry. 2 weeks from now, it's gonna be the week after the break. So, like,
Jesus. I'm about to say. No.
That's
the way he explained it.
So Monday,
No, it's not.
23rd,
It's 23rd.
23rd, not 16.
That'd be 20.
All right. Any question before we start? So we covered 4 cases where we have a damping on the system. 1, no damping when zeta equals to 0. Under damped when zeta is between 0 and 1. Critically damped and when zeta equals to 1. And over damped when zeta is greater than 1. So So when the system is under damped, where zeta is between 0 and 1, the response of the system is gonna look like x e power negative zeta omega n times t sine of omega n square root of 1 minus zeta square times t plus t, where it's going to be x naught cosine of omega n square root of 1 minus zeta square t plus v naught plus zeta omega n x naught 1 minus zeta square times sine of omega n square root of 1 minus zeta square t. So these are the same. I just have harmonic function, 2 harmonic function with the same frequency. I can add them up, come out with 1 amplitude and 1 phi. If this is A, if this is B, x would be s square root of a square plus b square, and the tangent of phi would be a over b. So this is what we covered on Monday class. So as you see, when we have underdamped system, you start the oscillation, and the motion is gonna decrease over the time until it's gonna die. So by if you have a system like this and you don't know about the zeta, so zeta is not known, but we know that it's an underdamped system because we can look at the motion of the system. By monitoring amplitude decreasing, so as you see, the amplitude has been decreased over the time. By monitoring that, we can find zeta. So how can we do that? Suppose this is the time that we are going to be at the peak, so x at time t1 is going to be capital X e negative zeta omega n t1 sine omega n square root of 1 minus zeta square t plus phi. And we know that this is the omega d, the frequency of the damped system. Omega n times this expression is gonna call omega d. This is x as t1, which is the this peak. Second peak is gonna be here. It occurs at t2, x at t2. So you know that you can see this. We can measure this by doing the experiments. So then you will go to the second cycle, second loop. Yeah, this is the second cycle. You can measure the second peak. It occurs at t2, x e negative zeta omega n t2 sine of omega d t2 plus phi. What's the relation between t1 and t2? T2 would be t1 plus 1 period of oscillation. T1 is here, 1 cycle later means 1 capital T. We are going to have T2. So now I'm going to write x T1 over x T2. I label this as a x1 and label this as a x2. X1 over x2 would be this divided by this, x e negative zeta omega n t1 sine of omega d t1 plus phi x e negative zeta omega n t2 sine of omega d times t1 plus t plus phi. I replace t2 here by t1 plus capital. So these two can be cancelled out, these two x. Omega d times capital T. Omega d is 2 pi over capital T. So omega d times capital T is going to be 2 pi. So this times this is going to be 2 pi. Sine of any angle plus 2 pi is going to be the same as sine of that angle. So because you are going to complete one loop. So this omega d times t1 plus omega d times t plus phi is going to be same as sine of omega d t1 plus phi, which is same as this one on the top. What I did is I multiplied omega d by t1, which is here, plus omega d times capital T, which is going to be 2 pi. And this 2 pi is not going to change the phi plus omega d t1. So I'm going to remove 2 pi from it. So I can cancel out these two as well. What is left is e power negative zeta omega n t1 divided by e power negative zeta omega n times t1 multiplied by e negative zeta omega n capital T. So T1 plus capital T. So these two are the same. I can cancel them out. So x1 over x2 is gonna be 1 over e negative zeta omega n capital T. This has negative here, it's going to be e power positive zeta omega n t. So if I apply the natural logarithm, ln of x1 over x2, it's going to be ln of e power zeta omega n t. ln of e power zeta omega n t is going to be zeta omega n t. So we define delta as ln of x1 over x2. It's gonna be zeta omega n capital T d. This is capital T d. Let me just for damped system. Because we have capital T for undamped system, TD is for damped system. So left side, you can measure that. You can measure x1 by doing the test. What would be the peak at a first peak? You can measure that. What would be the peak on the second cycle? x2. So you have this. On the right side, omega n is s square root of k over m. So let me simplify that a little bit. So delta, which is now, would be zeta of omega n. Td is 2 pi divided by omega d. And omega d is omega n times s square root of 1 minus zeta squared. We cancel out omega n, we will get zeta divided by s square root of 1 minus zeta squared times 2 pi. So left side it's noun, this ratio is noun. Right side, the only term which is not noun is zeta. You can square them, delta squared would be zeta squared divided by 1 minus zeta squared, 4 pi squared. Then multiply these two, delta squared minus delta squared, zeta squared equals to 4 pi squared, zeta squared. Then you are going to get delta squared would be 4 pi squared plus delta squared times zeta squared. So you can find zeta. So by monitoring the rate of amplitude decay, you can find zeta. Make sense? Let me keep that part. I'm gonna work on one example of this. So here I monitor the amplitude decay between x1 and x2. What if I study between x2 and x3? Am I going to get the different result? I mean, am I going to get the different delta, or it's going to be the same. Here I got delta equals to zeta omega and t. So if I go from x1, if instead of comparing x1 and x2, I compare x2 and x3 and say ln of x2 over x3. This peak and this peak. Two the other two cycles. Am I gonna get the different results? We are gonna get the same result because here, if I change xt3 here, this is gonna be the amplitude of the response, which is not gonna change. T1 is gonna change to T3, it's gonna change to T3. So T3 is gonna be T1 plus T2 plus TD. So the same logic, the same logic can be applied for this one. So you can cancel out these two. Instead of having T1, I'm gonna have T2. Instead of having T2, I'm gonna have T2 plus capital T. I can cancel them out. Here I'm gonna have T2. Here I'm gonna have T2 plus this. So I can simplify them. At the end, I'm gonna get the same thing. So no matter which two cycles you are comparing, as long as you are following cycles, you will get the same things. So by saying that, we can work on this example. Suppose we have an electronic instrument with the mass of 1 kilogram. It has been supported by two springs with a stiffness of 1200 Newton per meter and one damping of C. So it's an electronic instrument. It has been supported by two springs and one damper. The problem has two parts. First, part A, it's asking for natural frequency of the system and critical damping coefficients. So natural frequency, find the natural frequency and critical damping constant, means Cc. So natural frequency meaning omega n, you should find for mass and spring systems, mass and spring, you should find the equivalent stiffness divided by mass, then you can find the natural frequency. So these two springs are in parallel because they have the same deflection while the system is moving. So these two are parallel. So in parallel, we add them up. So we add two spring stiffness, so it's going to be 2400, one damper, and this. So 2400 divided by 1 square root, the unit will be in radian per second, 49 radian per second. So this is natural frequency. We don't need to know about C because we didn't ask, I didn't ask about the damped natural frequency of the system. So for critical damp, it's CC. I can write the CC in different forms. C over CC would be zeta. If I have zeta, if I have C, I can find CC, but I don't have. So I can say CC would be 2m times omega n. So we have shown that CC critical damping constant is 2 times n times omega. 2 times 1 times 49. It's going to be 98 Newton second per meter. How did I find the unit of the C? You don't need to memorize that. How can we find the unit of C? Force divided by velocity, because C, the damping is C times x dot. So the unit of the C would be whatever is the unit of F, which is Newton, divided by unit of the velocity, which is meter per second. So it's going to be Newton times second divided by meter. So this is how I write this. So you don't need to divide. Second part, suppose we do the test. We move it from relaxed position and release that. And then we notice this is x naught. Second cycle is x1. This x2, x3, and this is x4. Next cycle, like this. x0, x1, x2, x3, and the next one is x4. If the ratio between the first cycle and 4 cycles later, between this cycle and 1, 2, 3, 4, the 4th cycle later is 3. So if x naught over x 1, 2, 3, 4, 4 is 3. Find, we just apply the test and measure, I noticed this ratio. By doing the experimental thing, we noticed that the ratio between the first cycle and 4 cycles later is 3. Find the damping constant of the system, or zeta. They are the same. So this is the question. Good. So it's similar to what we did here, except here delta was the natural logarithm between two following cycles between x1 and x2. So if we were given between x1, for example, x0 and x1, we could simply use that. Or even between x3 and x4, or x4 and x5, we could find that. But we were given between x0 and x4. What should we do? delta, before we go through the delta. So x naught over x1, this over this, it's gonna be same as this over this. I just and x1, x2 is gonna be same as between x2 and x3. And x3 over x4. Good? These ratios are the same. This between this between this, and this, x3 and x4. So the natural logarithm of if this is delta, I can write e power delta equals to x1 over x2. So I can write x naught over x4 as a x naught over x1 multiplied by x1 over x2 multiplied by x2 over x3 multiplied by x3 over x4. If you cancel them out, you will get the x naught over x4. But all terms, each term that I have here is e power delta. X naught over x1 is e power delta. So this guy, x naught over x4 is 3, is going to be e power delta, e power delta, e power delta, e power delta. It's going to be e power 4 delta, which is 3. So ln of 3 is going to be 4 delta. And delta is this guy. One minus zeta squared times 2 pi. So if I solve for that, ln of 3 squared I'm gonna square this side multiplied by this, both sides squared, then I solve for zeta. So ln of 3 squared times 1 minus zeta squared would be 16 zeta squared times 4 pi squared. So it's going to be ln of 3 squared plus 64 times pi squared times zeta squared equals to ln of 3 squared. So zeta is going to be this divided by this. If I do math, I will find zeta equals to 0.043. Positive and negative, but negative is not acceptable because it's a ratio. Good? Any question on this? So let me question on this. Let me work on another example. So we have a water level meter like this. There is a bar with the arrow which is representing the level of water. And here we have a damper. And right here for the arm, we have a cylinder which is going to be in the water. So it's a mechanism for water. It's going to measure the level of water. So when it's at equilibrium, it's going to show the level of water. If you just push this cylinder into the water, so by X, so if you push it by the magnitude of the X, how much force is going to apply to the cylinder from the water? Do you recall that from the physics? If I push it when it's at equilibrium, it's suspended at this level, just push it by the X applying force. How much force is going to apply to the cylinder? Pardon?
Displacement of water.
The force coming from the water, it's gonna be, it depends on the density of the liquid, which is here, whatever is the density of the water, 1,000 kilogram per meter square, times G, the gravity, and the volume that you push in the water. How much would be that volume? It's going to be the cross section. Volume force would be rho G times V. Volume would be pi R square times X. True? You push this volume into the water, so it's going to apply this force against that. You remember this. So now let me replace volume with this. It's going to be rho density G times pi R square times X. Good? So rho is constant, it depends on the density of the water, of the liquid. G is constant, pi is constant, R is constant. The thing which is changing is X, and it has a linear relation with the F. So I can say the force has a linear function with the X, which is a deflection. So what I can do is, I can replace this part with a spring. True? Because it's showing the water is acting as a spring. So I'm gonna have this mass K from Y. And what would be the stiffness of this? This is going to be K of water. It's going to be rho G times pi times whatever is the radius of this cylinder. Good. So we were asked. So now, if you push this by x naught and release that, just push this and release that, it's gonna start oscillating. We would like to find a natural frequency of the system. Find and CC, critically damped constant. So let me talk about dimensions. This arm A is 0.075 meter. This arm is L 0.25 meter. The radius of this cylinder is 0.025 meter, 25 centimeter. And what else? The density of the water is 1,000 milligram per. Okay. Any questions so far? So let me first find the KW. It's gonna be 1,000 times 9.8 times pi 0.025 squared. It's gonna be 19.26 Newton per meter for the stiffness of the spring. Second thing is finding the equation of motion for the system. Then I'm gonna find K, equivalent K, and then I'm gonna find the natural frequency of the system. So suppose this bar is at the angle of theta. So the mass that we have here So the force, if this is theta, this distance would be a times theta. So the velocity, if this is y would be a times theta. Y dot, it would be a theta dot, and this x is gonna be L times theta. So you extended this, you extended the spring, so the force is gonna be in this direction, it's coming up, so the force coming from the damper, it should be in the opposite side of the motion. It's going up because it has theta. So now I'm gonna write the second Newton's law for the torque against point O. Summation of the bending moment, summation of the moment about point O, it's gonna be force Fk multiplied by distance, which is L. It's gonna be clockwise, so it's gonna be negative. Clockwise, it's making clockwise rotation negative. Minus this force times this distance. The force is gonna be C A theta dot, C times Y dot, times A, whatever is there. So the moment is this, coming from the stiffness, coming from the damping. This should be J with respect to O theta double dot. So I have a massless bar with one single M at the end. The J O would be ML squared. Because it's a massless, there is no mass for the bar. I have a just one mass located at the end of the bar. So what would be the J with respect to this? It's going to be ML squared. So if I rewrite this equation again, I'm going to get ML squared theta double dot plus CA theta dot CA squared theta dot plus Fk would be K times the distance or deflection, K times L theta times L is going to be K L squared times theta equals to 0. So this is going to be the equation of motion for this device. So what was the omega n? The omega n is whatever is the coefficient of theta or x, which is this, capital K, divided by whatever is the coefficient of x double dot or theta double dot. So I'm gonna have KL squared divided by ML squared. Cancel out these two, it's going to be square root of K over L. K, I already calculate that. 19.26, and M is 1 kilogram. So the angular frequency of the system would be 9.81 radian per second. Any questions so far? So the last part is finding CC. CC, the critical damping is 2m omega 2 m times omega. Don't put the mass. It should be whatever is the coefficient of theta double. So it's going to be 2 times m squared times omega n. So 2 times 1, L is 0.5 square, 0.25. And omega n is 9.81. The I don't have the number, but the unit is going to be Newton second.
Is there a conversion to the natural frequency?
Say it again.
Do you have the square root of 19.26 equals 9.1?
I made mistakes. Okay, where did you find K? Yeah, it's not 79.1.
It's 4.38.
Say it again.
It's 4.38.
Thank you.
39.
Any question on this? All right, let me work on one pulley system which has a damping also. We would like to find the natural frequency of pulley system. So we have something like this. K1, K2, pulley 1, pulley 2, and mass M. We would like to find the natural frequency of the system. So if the weight of this mass is W, which is the weight, entire of the rope is gonna see W. So this rope is gonna see W, pulley 2. Pulley 1 is gonna see W, entire of the rope. Rope cannot have different tensile force. So if this is W, this is W, the force coming to here is gonna be 2W. Same things here. It should be 2W. So this 2W is making some deflection on this. How much would be that? Force divided by K2. Force is 2W. Stiffness is K2, and delta 1 is force divided by K1, which is 2W divided by K1. This is what we know. Good? Makes sense? So now, if this spring is moving by delta 2, if this spring is moving down by delta 2, how much would be the motion on the end? What would be the x? Just forget about this. If I have only this pulley, if the center of pulley is moving down by delta 2, what would be the relation between delta 2 and x? We have worked on this problem before for these types of the pulley. So 2 of delta 2 is going to be x. So the center of this pulley, if it's moving by delta 2, this rope, which is representing x, is going to move by twice. So by moving up this, we are going to have this. By moving up this, we are going to have 2 times delta 1. So 2 times delta 1 plus 2 times delta 2 is going to give me the total deflection of the mass M. So these two, they are going to make a deflection, displacement on mass M. Whatever deflection here, twice of that is going to make this deflection, this displacement, plus twice of delta 2 is going to be added to the previous displacement. So 2 of that plus 2 of delta 2 is going to make my x. So if I want to replace the entire of this with spring and mass, if this is moving by x, k equivalent also is moving by x. So so W would be k equivalent times x. I'm gonna replace x by this, so k equivalent times 2 delta 1 plus 2 delta 2 equals to W, and delta 1 is this. It's gonna be k equivalent would be 2 times delta 1, 4W divided by k1 plus 4W divided by k2 equals to W. If it's moving by x, the force should be equal to the weight. So I can cancel out this W, and k equivalent would be 1 divided by 4 times 1 over k1 plus 1 over k2. Or k equivalent would be k1, k2 divided by 4 k1 plus k2. I was asking for natural frequency of the system. What is the k equivalent? I put it there. K1, k2 divided by 4 k1 plus k2. What is the m? Just 1m. Any question before we start the last exam? Something like this was on the one of the exams one. So it wasn't last year, but so suppose there is one mass, small mass, and another big mass. I need to talk about some concept before we do the example. So this mass has a speed of mass 1 mass this mass has velocity of m at time 1. So suppose it's moving by the 20 meter per second speed, so it's gonna hit the bigger mass. So what's gonna happen? It's gonna hit that, it's gonna back in the opposite direction, and this guy is gonna move to the other direction. So this is what's gonna happen for this problem. What we know that the momentum of this momentum, remember momentum. It's a mass times V of m1 minus V of m2 is gonna be equals to the momentum of this. Whatever momentum we had before, after it's gonna hit this, we should have this one to keep the momentum constant. So Vm1 is speed or velocity before, Vm2 is velocity after for mass, for a smaller mass. So Vm1 is velocity of mass before, which is going to be 0 in this case because it's at the next position, so it doesn't have a speed. So Vm2 would be velocity of mass m after. So what we know that Vm1 is 0, but we don't know anything about, we know Vm1 is given, but we don't know anything about these two. What's gonna happen after this mass is gonna hit the bigger one? There is a coefficient, we call it reciprocation. It's in dynamic, I call it with the epsilon, reciprocation coefficient. It's gonna help us to find that. This is gonna say that this reciprocation coefficient is defined as negative relative velocity of separation divided by the relative velocity of approach. So relative velocity of separation is defined as this guy, Vm2 separation, negative Vm2 capital M minus Vm2 capital, lowercase m2 divided by Vm1 minus Vm1. When they are approaching, what would be the relative velocity? 1 is meaning they are approaching. 2 representing after they hit. So we call it reciprocation coefficient. So this, if you have this coefficient, we can find the equation for the relation between relative velocity of separation versus relative velocity of approach. So we need to know this before we go through the example. Now we can work on this interesting example. So suppose we have a hammer and anvil. So there is a hammer on the top. And one anvil here, capital F. We represent the foundation as a spring and damper. So the foundation of the anvil is can be represented by a spring and damper, and this is for the top or hammer that you drop. So this is 2 meter. K is 5 meganewton per meter square. C is 10,000 newton second per meter. These are the coefficients. These are the specification of the system. And the weight of this is 5,000 newton. And this top is 1,000 newton. The weight. So this is the question. When you drop the top or the hammer, it's gonna speed up until it's gonna touch the anvil. Then after it's gonna hit the anvil, it's gonna go up, and this is gonna going down. So we are gonna having something like this. So one small mass is gonna hit the bigger one. So the momentum should be the same before and after. So we can use that equation, and the respiration coefficient is given by 0.4. So this is given. So this is given. So by this information, we would like to find the response of the system. Basically, I'm looking for this function, x of t. What would be the response of the system for angle after the top is gonna hit them? So we are gonna work on this example after the break. So I'm gonna post, maybe I already posted the homework, the new homework, which is due after the break. And I'm gonna collecting the new homework today.